Welcome to part 5 of our camera training series, Camera Integration. So far, we have explored camera fundamentals, different camera types, image formation, and image quality. Now we move to the stage where the camera becomes part of the complete vehicle system. In this section, we will understand how cameras are connected, integrated, coordinated, calibrated, installed, and selected for different operational roles. This is where individual camera knowledge comes together to create a reliable and effective vision system for an unmanned ground vehicle. Welcome to part 5 of our camera training series, Camera Integration. In this final part, we move beyond the camera itself and study how it becomes part of a complete vision system. First, we will understand video encoding, how raw camera footage is compressed to reduce bandwidth and storage without losing critical visual information. Next, we will explore video streaming, how live video is transmitted from the camera to onboard computers, operator consoles, and remote control stations. We will then study camera interfaces, which define how cameras physically and electronically connect to processors, networks, and vehicle systems. After that, we will examine video performance, including bandwidth, latency, resolution, frame rate, and coordination between multiple cameras. Finally, we will cover camera installation, how placement, calibration, orientation, field of view, blind spots, mounting, and power integration affect real-world performance. Part 5 brings all the earlier camera concepts together into one reliable, connected, and mission-ready camera system. Let us begin by understanding what video compression is. A camera produces a large amount of video data, especially when it is recording at high resolution and high frame rates. Video compression reduces this data so that the video becomes easier to store, transmit, and process. In simple terms, it makes video more manageable for storage systems, onboard computers, and communication networks. Now, how does video compression work? A video is made up of many individual frames. In most cases, large parts of the scene remain similar from one frame to the next. Compression identifies this repeated information and avoids storing or transmitting it again unnecessarily. It can also simplify similar areas within a single frame. As a result, the system mainly focuses on the important changes, such as the movement of the UGV, another vehicle, or a person in the scene. This significantly reduces the overall amount of video data. Now, let us understand why video compression is needed. Video compression reduces the bandwidth required to transmit camera feeds and also lowers the amount of storage needed for recording. This helps live video stream more smoothly and allows several camera feeds to operate together on the same vehicle network. It is especially important when video must travel over a wireless radio link with limited capacity. However, compression always involves a trade-off. Higher image quality preserves more detail, but it also requires more data, bandwidth, storage, and processing power. Stronger compression produces a smaller video stream, but some visual detail may be lost. If compression is too high, edges may appear blurred, small objects may become difficult to identify, and important scene information may be hidden. Video compression breaks each frame in 3 different types of frames. Let us understand the 3 main frame types used in video compression: I-frames, P-frames, and B-frames. An I-frame is a complete image. It stores the full vehicle scene and acts as a reference for the frames that follow. Because it contains the entire picture, it requires the most data. A P-frame uses an earlier I-frame or P-frame as a reference. Instead of storing the whole landscape again, it mainly records what has changed, such as the vehicle moving forward. A B-frame goes one step further. It compares both earlier and later reference frames and stores only the remaining differences.
This usually provides the highest compression efficiency.
In simple terms, I-frames store the full image. P-frames store changes from the past. B-frames predict changes using both past and future frames. Let us now understand how I, P, and B frames are arranged in a video compression sequence. The sequence begins with an I frame. This is a complete reference image and can be decoded independently. The following B-frames do not store the full scene. Instead, they use information from both an earlier frame and a later reference frame. This is called forward and backward prediction. A P-frame is then created by predicting changes from a previous I-frame or P-frame. It stores mainly the movement and differences rather than the complete image. The same pattern continues through the video. I-frames provide fresh reference points, P-frames predict from the past, and B-frames use both past and future references. This frame structure significantly reduces video data, but using more predictive frames may also increase processing and latency.
Let us now understand a group of pictures, or GOP, in video compression. A GOP is a repeating sequence of I, P, and B frames. It normally begins with an I frame, which stores a complete image and acts as a reference. The following P and B frames reduce data by storing mainly movement and changes instead of the entire scene. After a certain number of frames, another I frame is inserted to create a fresh reference point. This is important because predictive frames depend on earlier frames. If packets are lost or an image becomes corrupted, the error may continue across several frames. A new iframe allows the decoder to recover and rebuild the video correctly. More frequent iframes improve recovery and reduce seeking time, but increase bandwidth. Fewer iframes improve compression, but may increase recovery time and dependency between frames. Ideal GOP length depends on application, but typical group of picture or GOP sizes between iframes might be 30 or 60 frames, or 25 or 50 frames depending on region. Let us now compare the three major video compression standards, H.264, H.265, and H.266. H.264, also called AVC, is the most mature and widely used of the three. It offers a good balance of video quality, processing simplicity, compatibility, and reliability. However, it generally requires more bandwidth than newer formats. H.265, or HEVC, improves compression efficiency. It can deliver similar image quality at a lower bitrate, making it useful for high-definition and multi-camera systems. The trade-off is that it needs more processing power. H.266, also called VVC, is the newest standard. It offers the highest compression potential and is aimed at future high-resolution systems. However, it is also the most demanding in terms of computing power and integration. In simple terms, H.264 focuses on compatibility, H.265 improves efficiency, and H.266 pushes compression further for advanced applications. Let us now understand how H.264 video compression works. H.264 first divides each video frame into smaller blocks. It then compares these blocks within the same frame and across consecutive frames to identify repeated information. Instead of sending every frame as a completely new image, H.264 mainly records what has changed. The compressed video is then converted into a compact bitstream for storage or transmission. Let us now understand H.265 compression, also known as HEVC. H.265 is the successor to H.264 and is designed to reduce video size while preserving useful image quality. It is particularly suitable for HD, 4K, and multi-camera systems. It works by dividing each frame into flexible image regions, predicting repeated information within the same frame and across consecutive frames, and using motion vectors to describe movement. The remaining data is then converted into a smaller compressed bitstream. The main advantage of H.265 is better compression efficiency. It can deliver similar image quality at a lower bitrate, which helps reduce bandwidth and storage requirements. Let us now understand H.266 compression, also known as versatile video coding, or VVC. H.266 is a newer video compression standard designed to reduce video size while preserving useful image quality. It is particularly suited for high-resolution video and future multi-camera systems. It works by dividing each frame into flexible regions, predicting repeated information within the same frame and across multiple frames, and using advanced motion estimation to describe how objects move. The remaining information is then converted into a smaller, compressed bit stream. The main advantage of H.266 is higher compression efficiency than H.265. This can reduce bandwidth and storage requirements while maintaining similar visual quality. For unmanned ground vehicles, H.266 could support more camera feeds, high-resolution surveillance, and longer mission recording. However, it requires more processing power and integration effort, and must be carefully evaluated for low-latency driving video.
Video encoding can be performed at different points in the camera system. Some cameras include an onboard system on chip, or SoC, that compresses the video before transmission. Encoding can also be handled by the main compute platform, such as an NVIDIA Jetson, using its dedicated hardware encoder. A third option is software-based encoding, where the compression is implemented through programming on the processor. For most military vehicle architectures, the best default is use the camera to perform ISP processing, but perform video encoding on the onboard compute platform, such as a Jetson, using its dedicated hardware encoder. This arrangement provides several advantages. One central place to configure all camera streams. Easier synchronization and timestamp management. Ability to run AI before encoding. Avoid pure software encoding on the CPU for routine multi-camera real-time operation. It can consume substantial processing capacity and add unpredictable latency. Software encoding is better suited to prototyping only. We have now completed the topic of video encoding and understood how camera footage is compressed for efficient transmission and storage. Next, let us move to video streaming, where we will explore how live video travels from the camera to onboard computers, operator displays, and remote control stations in real time. Now let us understand streaming protocols. A streaming protocol is a set of rules used to deliver live video from a camera system to another device over a network. In a UGV, the video is first captured by the camera and compressed by an encoder. The streaming protocol then carries that video through the onboard network and wireless radio link to the ground control station. It also helps manage packet delivery, frame timing, stream control, and recovery from packet loss. The choice of protocol affects latency, reliability, bandwidth usage, and video quality. This is especially important in remote driving, where the operator must receive clear and timely video. Simply put, compression reduces the video size, while the streaming protocol decides how that video travels across the network. Now let us compare the main types of streaming protocols. RTSP, or Real-Time Streaming Protocol, is commonly used to access and control video streams from IP cameras, while RTP normally carries the actual real-time video packets. RTP, or Real-Time Transport Protocol, is an internet standard used to deliver audio and video over IP networks. WebRTC is designed for extremely low latency, interactive video. It is useful when a vehicle operator needs near real-time video through a browser or control application. SRT and RIST focus more on reliable video delivery across unstable or lossy networks. They can recover missing packets, but this additional recovery may increase latency. For vehicle applications using a radio link, RTSP with RTP is commonly used because it is widely supported by cameras and video systems. Therefore, the final selection should balance latency, reliability, compatibility, and radio link quality.
Now let us understand why RTP over UDP works well for unmanned ground vehicle camera video. The camera first captures the scene, and the video is compressed using H.264 or H.265. RTP then adds sequence numbers, timestamps, frame timing, and packet loss information. UDP transports these packets quickly through the radio link to the ground control station. The main advantage is low latency. UDP does not wait for retransmission, so the operator continues receiving the latest video instead of waiting for a perfect older frame. This makes RTP over UDP suitable for teleoperation, navigation, and manipulator cameras. However, packet loss can reduce video quality. Therefore, it works best when low latency is the top priority and the radio link is reasonably stable.
We have now completed video streaming and understood how live camera feeds are transmitted across the vehicle system. Next, let us move to camera interfaces, where we will look at how cameras connect to processors, networks, and other onboard systems for reliable video and data transfer. Now let's understand camera interfaces. A camera interface is the communication link between the camera and the rest of the vehicle system. It connects the camera to an onboard processor, recorder, or display. This connection carries more than just video. It may also transfer camera control commands, synchronization and timing information, health status, and sometimes electrical power. The choice of interface is important because it affects bandwidth, latency, cable distance, reliability, and compatibility with the processor. In an unmanned ground vehicle, the video typically moves from the camera through the camera interface to the onboard processor and then to the display recording system. Simply put, the camera interface is the data highway connecting the camera to the unmanned ground vehicle. Now let us compare the main camera interfaces used in unmanned ground systems. USB is simple and easy to integrate, making it useful for prototypes, testing, and laboratory setups. Ethernet is more scalable and works well when several IP cameras must be connected through a common vehicle network. MIPI CSI provides a short, high-speed connection directly to an embedded processor. It is suitable for compact onboard AI computers, but cable length is limited. GMSL and FPD-Link are designed for automotive camera integration. They support longer cable runs, low latency, synchronization, and strong resistance to electrical interference. SDI provides a reliable, dedicated video connection and is mainly used in professional monitoring systems. For production unmanned ground vehicles, GMSL or FPD-Link are generally recommended for rugged navigation and perception cameras.
Now let us understand a GMSL camera. GMSL stands for Gigabit Multimedia Serial Link. It is a high-speed camera interface designed mainly for automotive, industrial, and rugged vehicle applications. In this system, the camera captures video, and a serializer converts the video and control data into a high-speed serial stream. This data then travels through a single coaxial or shielded twisted pair cable. At the processor end, a deserializer reconstructs the video for processing, display, recording, or AI use. The major advantages of GMSL are long cable reach, high bandwidth, low latency, strong resistance to electrical noise, and simplified wiring. A single cable may carry video, control signals, and power. However, GMSL systems can be more expensive and complex. They require dedicated serializer and deserializer hardware and may depend on specific vendor ecosystems. For production unmanned ground vehicle, GMSL is an excellent choice for rugged navigation and perception cameras.
We have now completed camera interfaces and understood how cameras connect with processors, networks, and onboard systems. Next, let us look at video performance, where we will examine how bandwidth, latency, resolution, frame rate, and multi-camera coordination affect the quality and responsiveness of the video system. Let us understand bandwidth requirements in a multi-camera vehicle system. Bandwidth is the amount of data that must be carried every second to transmit video reliably. It is normally measured in megabits or gigabits per second. The required bandwidth increases with higher resolution, higher frame rate, lower compression, and more complex or fast-moving scenes. In a multi-camera system, the total load is the combined bitrate of all active cameras. For example, 4 cameras operating at 4 megabits per second create a 16 megabit video load. Additional capacity is still required for telemetry, control traffic, network overhead, and sudden bitrate peaks. If bandwidth is insufficient, the system may experience dropped frames, video freezes, higher latency, and poor camera synchronization. Therefore, the network should be designed for both average and peak demand, with enough spare capacity for reliable operation. Let us understand end-to-end video latency in a vehicle camera system. It is the total time taken from the moment a camera captures an image until that image appears on the operator's display. This delay is created at several stages: camera capture, image processing and encoding, transmission through the onboard network or radio link, decoding at the receiver, and final display rendering. Among these, network delay can vary the most depending on bandwidth, distance, signal quality, packet loss, and buffering. Low latency is critical for situational awareness, obstacle avoidance, precise vehicle control, and real-time AI processing. Excessive delay can make the operator react too late. Latency can be reduced through efficient encoding, low-latency communication links, hardware acceleration, optimized processing pipelines, and faster displays. The goal is simple: deliver the video as quickly and reliably as possible. Let us understand the synchronization of multiple cameras in a vehicle. Synchronization means that all cameras capture frames at the same instant or with a precisely known timing relationship. This ensures that the front, rear, left, and right camera feeds represent the same moment. This is important for surround view, stereo depth calculation, sensor fusion, and AI perception. When the frames are time-aligned, the system can compare and combine them accurately. Synchronization can be achieved using a common hardware trigger, a shared system clock, accurate timestamps, and software-based frame matching. If the cameras are not synchronized, moving objects may appear in different positions across the feeds. This can cause poor image stitching, depth errors, and delayed or incorrect decisions. In simple terms, good synchronization improves the accuracy, reliability, and safety of the complete unmanned ground vehicle vision system. Let us understand timestamping and trigger synchronization in a multi-camera vehicle system. Timestamping assigns an exact capture time to every video frame. This allows the onboard computer to identify when each image was taken and align frames from different cameras during processing. Trigger synchronization works differently. A common electrical trigger signal is sent to all cameras, causing them to capture an image at nearly the same instant. This creates true capture time alignment. These two methods work together. The trigger controls when the cameras capture, while the timestamp records when each frame was created. Accurate timing is essential for surround view, stereo depth, sensor fusion, and AI perception. Without it, moving objects may appear in different positions across camera feeds, leading to poor alignment and unreliable decisions. We have now completed video performance and understood the key factors that influence video quality, responsiveness, and multi-camera operation. Next, let us move to camera installation, where we will look at how camera placement, orientation, calibration, mounting, and power integration affect the overall effectiveness of the vehicle's vision system. Now let us understand why camera placement matters on an unmanned ground vehicle. The position of each camera determines what the vehicle can see during navigation, reversing, obstacle detection, teleoperation, and surveillance. Poor placement can create blind spots, blocked views, or limited visibility close to the vehicle. A typical vehicle may use several camera locations. Front cameras support driving and obstacle detection. Rear cameras improve reversing and rear awareness. Left and right cameras help with side clearance and turning. A mast-mounted camera provides a wider and longer range observation view, while a camera near the manipulator or payload supports close-up inspection and precise operation. Therefore, camera placement should always be based on the specific function of each camera and the coverage required around the vehicle. Now, let us look at mounting height, orientation, field of view overlap, and blind spots. A low-mounted camera gives a better view of nearby ground obstacles such as rocks, curbs, and trenches. However, its overall viewing distance is shorter. A high-mounted camera improves long-range visibility and situational awareness, but it may miss obstacles very close to the vehicle. For navigation cameras, a slight downward tilt, typically around 5 to 15 degrees, helps the camera see both the path ahead and near-ground obstacles. Field of view overlap is also important. Front, rear, and side cameras should overlap enough to reduce gaps during turning and close maneuvering. Even with multiple cameras, blind spots may remain near the vehicle corners or body panels. Therefore, camera height, angle, and overlap must be designed together to provide safe and continuous coverage.
Now let us understand blind spots in a vehicle camera system. Blind spots are areas around the vehicle that the operator or camera system cannot see clearly. They are usually caused by limited camera angles, poor mounting height, or obstruction from the vehicle body and payloads. Good camera placement helps reduce these hidden areas. Front and rear cameras provide basic driving coverage, while side cameras improve visibility during turning and close maneuvering. A higher-mounted mass camera can add wider situational awareness. The views should overlap, especially near the vehicle corners, so that gaps between cameras are minimized. Cameras should also be tilted slightly downward, kept clear of obstructions, and positioned where they can be protected and cleaned easily. Good placement improves safety and teleoperation. This brings us to the end of Part 5, Camera Integration. In this video, we covered how video is encoded for efficient transmission, how live video is streamed across the vehicle system, and how different camera interfaces connect cameras with processors and networks. We also looked at video performance, including bandwidth, latency, frame rate, resolution, and multi-camera coordination. Finally, we discussed camera installation, including placement, calibration, orientation, blind spots, mounting, and power integration. With this, we also conclude our complete video series on navigation camera understanding. Thank you very much for attending and following the series. I sincerely hope you found these videos useful, informative, and relevant to your work.